So, today we will summarize all the previous talks in the next three talks. So, we have discussed, we have first discussed the metric defined on a non-empty set X. That is, we used the fundamental rules of distance and then we defined a function d on a non-empty set x cross x to R which satisfies these four fundamental properties, and then we say that d is a metric on this one. So with respect to this metric, by using this rule to calculate the distance between any two element in a set. So you can say that this d which we have defined, and which satisfies these four properties. So by this rule, that is to say, you have any rule which satisfies these four properties, by which we can calculate the distance between any two point in a non-empty set X. And then we have seen several examples, and we have seen several examples of a metric, and a set with a metric. It is called a metric space. So here is we have several examples we discussed over here, and then what we have done, we have seen that several exercises we have seen, and then we have discussed the distance from a point to a set and the diameter of a set. So the diameter of a set is you can take the diameter of the set is you take the supremum of dxy between any two element. That is the diameter, and the distance from between two sets, you take the infimum of all the points. For example, we can take suppose here this is your set. So you take all this point, you take all the point, you take this and this and this, and then you take the supremum of all their distances, that is the diameter of the set, And the second one is we have discussed the distance between any two sets. So if you have suppose this set is your A and here you have set B, then the distance between these two sets, you take all the sets, take all these sets and take the infimum of all these distances. And of course, keep in mind, we are calculating the distance which we have defined with respect to this d, and this d is what? This d is the metric on x. So there is a possibility, as we have seen, that if we are considering what with respect to one metric, the distance may be something, and with respect to the other metric, the distance may be different from the distance from the other metric. That we have seen in our example which I mentioned. So let me see here is for example, if you have here you can see you have this is your subset S of R2, and here is with respect to the usual metric, the diameter of the set is this thing. The diameter of the set is this thing, and the diameter with respect to the taxicab metric is equal to this plus this is equal to 2, and the diameter with respect to max metric is equal to 1. So with respect to different matrices, we can see that the diameter is different, and similarly we can see that the distance between any two point, the distance between any two sets, it will be it's not necessary to be same with respect to different matrices. So it could be different with respect to different matrices on a non-empty set X. And then we have mentioned that if you have a metric space XD, okay, and then with the help of this D, we can define several matrices, okay. Namely, we can define the matrix D1 in this way and D2 in this way. And then with respect whether D is a metric, D is a bounded metric or not. Bounded means that the diameter is finite with respect to the metric D. So whether this set, the set X with respect to this metric is bounded, is bounded or not, it's no matter, but the metric this space X with respect to this metric and with respect to this metric is bounded. And then we have seen several examples, okay, and then we defined the open sets and the interior of open sets. And you see that we have seen the interior, the open set or open sphere. So we defined the open sphere with center at x0 and radius r, which is equal to the set of all points y in X such that the d x0 y is less than epsilon. That is to say, all the points, okay, within the radius, within the length from x0, within the length r, okay, r is strictly less than, okay, the length is strictly less than the r, okay. So these are the points in X whose distance from x0 is strictly less than r, okay. And this again we can see that here is this open sphere. This is our open sphere with center at x0 and radius r. It is depending, the shape of this depends on the D. So which kind of the matrix we are using. For example, in R2 we use the max matrix, taxicab matrix, usual matrix, discrete matrix, and so on and so forth. And we can define the closed ball. So the closed ball is this is the notation of the closed ball with center at x0 and radius r, which consists the set of all points y such that d x0 y is less than or equal to r. And then we have seen that with respect to different matrices, for example, with respect to this kind of matrices, okay, with respect to the matrix, this matrix, the open ball, this is the open ball in R2 with center at origin and radius is 1. So you will get this is 1. And with respect to the usual metric, with respect to the usual metric, keep in mind this is not the round, this is not the, and with respect to the usual metric you will have this one, and with respect to the max matrix you will have the ball like this one. And similarly, if you will consider the set of all real valued continuous functions defined on a closed interval, then the open ball with center at f0, f0 is a function in CAB with radius is r. So if suppose here you have this is your the dotted line, this is your dotted line is your f0, okay, this is your f0, okay, and then you add r plus here is, then you have this line, this, so this function is f0 t, so plus r, and then you subtract, so this function is your f0 t minus r. So the open ball with center at this function f0 is this shaded area, okay, with radius r, of course excluding this boundary this boundary function. And the closed ball you can include this boundary function. So you can see that and it is only when you are considering the sup matrix on CAB. So if you are considering the sup max matrix on AB, then this is the shape of an open ball with center f naught and radius r. And then we defined the interior point, open set, interior of a set. So here is a point. Suppose we are considering this set is metric space. Okay, this is your set A, and here you have a point X. So this point X is called an interior point of the set A if it is the center of some open sphere. Okay, it is the center of some open sphere contained in it. So that, in other words, if there exists R greater than 0 such that SRX lies within A. So you can see that lies within A. For example, if you are considering a point near here, for example, if we are considering, one can say that, okay, I am considering the point is here. Okay, whether this is an interior point or not. Yes, this would be an interior point. Why it would be? We can find a radius R. Okay, so you can treat the R is the distance from this point and to this boundary point. Okay, so you take the R is less than with this one, and then you can take a very small one, is something like this. Okay, so this would be an open sphere with radius R and center at this point. So then this point would be an interior point. So here is the important part is that it is the center of some open sphere, not all open sphere. Okay, and set of all interior points is called interior of a set, and a set A, this set A is called an open set if each of its point is the center of some open sphere contained in A. That is to say, a set A is open if and only if a set is open if and only if each of its point is an interior point of A, or it is the center of some open sphere contained in A. So, and this set A is called, the set A is called neighborhood of the point A, X, if there exists an open sphere centered at X contained entirely in this one. So, of course, if A is open, then it is called open neighborhood of X. So, this we have done, and then we have seen several examples. Okay, and we have proved several these properties of interior and closed set, and we have proved that every open sphere is an open set, and we proved that a subset A of X is open if and only if it is the union of open spheres. Okay, and then we have proved that arbitrary union of open set is open and finite intersection of open set is open. But the finite, the arbitrary intersection of open set need not be open. This we have seen, and then we have also proved that the interior of A is the largest open subset of A. Okay, and then we discussed the limit point. So, suppose X is your metric space. Okay, A is a subset of X, then a point X. Okay, it might not be in A. So, okay, so the point X, small x in capital X, is called a limit point of A if for every open sphere centered on X, okay, contains some point of A other than X. Contain some point of X other than X. So that's why you see here is every. So you take any, because here is if each open sphere. So any open sphere with center at its contains. So whatever is your alpha, whatever is your R, you take any R, and then you will see that whatever, for example, if you are taking R is very small, say for example, if R is this one, even then you can see that it is the center of the open sphere, and this open sphere contains points of A other than X. But if you take, suppose you are taking is far away, suppose this is your point X, whether this point X is a limit point of X? No, because if we are considering the open sphere, this one, okay, open sphere with center at X and radius is, this is your radius R, then it does not contain any point of A. But it is true for all. So if I take, suppose I say that, okay, I am considering this open sphere, okay, up to here, this open sphere, then it contains, but the question is that for the limit point, every open sphere, but this open sphere does not contain any limit, any point of A. Okay, so this is the definition. So this we have proved we have discussed the definition of a limit point, and the set of all limit points is called the derived set. And then we discuss several examples, okay, and several properties, and then we define the closure of A. Closure of A is the set of all points of A and the derived set. Okay, so the union of the set A and the derived set, it is the closure of set A. And this is a very important result which we have proved, that X is the limit point of A if and only if the distance from X to A is equal to 0. Then a set is closed. A set is closed if and only if it contains all its limit points. A set is closed if and only if it contains all its limit point. Or in other words, we can say that a set is closed if and only if the closure of A is equal to A. And then we prove that a set A is closed if and only if its complement is open. And we have also proved that every closed sphere is a closed set. And then we proved that arbitrary intersection of closed sets is closed and finite union of closed sets is closed. But arbitrary union of closed sets need not be closed. This we have seen. And then we proved that the closure of A is the smallest closed subset of X containing A. Okay. And then we gave the definition of the boundary point. A point X, in capital X, it is called a boundary point of the set A if it is neither an interior point of A nor an interior point of complement of A. And then we discussed several properties of this one, and we have seen that here are several examples and properties we have seen. Okay, so we are not going to in the detail, and then we discuss the subspace. So the subspace means that if you have if you have a metric space XD, suppose you have a metric space XD, okay, it means that D is a function mapping from X cross X to R. Now, Y is a subset of X. If Y is a subset of X, and then dy is the restriction of D, that is to say dy xy is equal to d dxy for all xy in Y, then this is the restriction, dy is the restriction of X. Okay, so but this dy is again a metric because D is a metric, then Y dy is a metric space, and this is called a metric subspace of XD. Okay, and then we have discussed several results, properties, and we have seen the several things related to the subspaces. So again, here are several examples we discussed. Okay, and several results. The important thing is that how we can this lemma is very important. How we can say for example, if you have a set suppose here is suppose this is your metric space. Okay, this is a metric space X, and here you have a set A. Okay, and now suppose if you have a point small a, suppose this is your Y, you can take suppose this is your Y. Okay, now let us take a point. Suppose this is your point A in Y, and now you can define this is your ball with radius this one. So this ball is the same as I can take S A R dash. This is ball with respect to the metric on dy, and here you have the metric on this one. It is same as this it is same as d of S R X A. But suppose if you have a point here, this is your point A. Okay, now you have a ball. This is your ball with respect to SRA. That is to say, this is the open ball with center at A and radius R with respect to the metric D. Now, what would be the open ball? Okay, with respect to the metric dy in Y. So that is you take the intersection with Y. So that is intersection with Y. So you take this portion only, this one. You exclude this one. So this is the open ball SRA prime. That is to say, open ball with center at A, radius R with respect to dy or in Y. So this is a very important result or important concept, because all the time we will have to check whether we are considering the ball, closed set, or interior point or limit point in the whole space or in the subspace. Okay, so this we have done, and then we have several results related to this one. The second part is in the second chapter we discussed about the completeness of a metric space. So the completeness of the metric space means that we have seen that because in the real analysis we discuss about the convergent of the sequence. So in the convergent of the sequence we see that for every epsilon positive there exists a delta positive such there exists a positive integer n such that the mod of xn minus x is less than epsilon whenever n is greater than capital N. So that was the definition of a convergent sequence to a point x in a real analysis. Now how we can extend this definition to a arbitrary set, or in particularly you can say how we can extend it to a complete metric space. So to prove, so this we have seen. So here is we discussed, suppose you have a so xd be a metric space and xn be a sequence in X, and we say that this sequence xn is convergent if there exists a point x such that for each epsilon positive there exists a positive integer and such that the distance between xn and x is less than epsilon for all n is greater than n. Okay, and this point x is called a limit point. In other words, so we can write this definition in terms of the ball. That is to say, we say that the xn converges to a point x if for every epsilon positive there exists a positive integer n such that xn belongs to S epsilon x. So you have x1, x2, x3, xn. So after this capital N, n plus 1 must be, so you have for every epsilon positive. So you take any epsilon, according to you can choose n. So here is you have this one point x, suppose this is our epsilon, so this is the ball with center at x and radius epsilon. So after n, capital N, all the elements of the sequence will lie within this open wall. So for all n is greater than n, all the points this lies, all the points this lie in this open ball. So that was the definition of the convergent of the sequence. And then we have seen several examples of the convergent sequence, and we have proved that the limit of the convergent sequence is unique and every convergent sequence is bounded. This we have seen, and we have also seen that the very important result that if X is the limit point of A, which is a subset of a metric space, if and only if there exists a sequence Xn of points of A, none of which equal X, such that Xn converges to X. So this is a very important point. By using this important result, we can prove that whether a set is closed or not. Okay, in other words, you can take a sequence. Suppose you want to prove that the set A is closed, then you take a sequence of points and assume that it is converging to a some point X and prove that this limit point lies in A, then A is closed. So this is the way to prove the convergence, to closeness of the set.